Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 14, 2025, just yesterday. This paper investigates some really surprising claims about LLM reasoning, finding one model could correctly answer over 53% of math problems after seeing just 60% of the question. The paper is titled Reasoning or Memorization: Unreliable Results of Reinforcement Learning Due to Data Contamination, and the implications for model evaluation are quite significant. The authors argue these apparent reasoning gains aren't genuine, but are due to the model memorizing benchmarks that leaked into its training data. To kick things off, the authors show a really striking example of this memorization effect. They take a problem from the Math 500 benchmark and feed only the first part of the question, what they call a partial prompt, to two different models. The first model, QN 2.5, not only completes the rest of the question perfectly, it then solves it, providing the full reasoning and the correct answer. In contrast, the second model, Llama 3.1, seems confused and produces a completely wrong answer. This stark difference really drives home the core argument. So to really isolate reasoning from memorization, the researchers needed a test that the models couldn't possibly have seen before. And that's exactly what they did. They created a new, fully synthetic dataset called random calculation. Here we see two examples from it, a 5-step calculation and a much harder 10-step one. The key is that because these problems are generated on the fly, there's zero chance they leaked into any training data. This creates a clean, uncontaminated environment to truly test a model's arithmetic abilities. Moving on, these plots show what happens when the models are trained on the Math 500 dataset, which the authors suspect is contaminated. The models were trained using reinforcement learning, a method where they get feedback, or a reward, to improve their answers. They were given correct rewards, random rewards, and even intentionally incorrect rewards. For the two Quen models on the left, their accuracy stays high no matter what. But for the Llama model on the right, its accuracy only improves with correct feedback. This stark difference suggests the QN models aren't actually learning. They're just recalling memorized answers. This table then details the specific settings used for generating answers from the models. It shows 4 main configurations, varying whether they used greedy decoding, which is where the model just picks the most likely next word, or averaged 16 different attempts for a more robust result. They also tested with and without the official chat template, which formats the conversation. The other parameters, like temperature and top P, are knobs that control the output's creativity. This methodological detail is important because it shows the memorization effect wasn't a fluke. It happened consistently across different prompting methods. Alright, so this next table puts that idea to the test across several math benchmarks. It shows how well the models can complete and solve problems when given only a fraction, like 80, 60, or even just 40% of the question. The key scores are exact match, which is a perfect match, and rouge L, a score for overlapping text. On older datasets like Math 500, the QN models score incredibly high, but on newer ones like Live Math Bench, their scores drop to 0, just like Llama's. This pattern is the key evidence for memorization. So, to really nail this down, the authors trained the models on their clean, synthetic, random calculation dataset. These plots show what happened during that training. The green line shows that with correct rewards, both the QN and Llama models learn and improve their accuracy. In fact, they even surpass the max at 16 baseline, which is the best score from 16 separate attempts. But when given random or incorrect feedback, represented by the other lines, their performance goes nowhere or collapses. This identical pattern, seen across both models, shows the magical learning effect completely disappears on a clean dataset. So, putting it all together, the conclusion is pretty clear. The seemingly magical ability of the Quen models to learn math from random or even wrong feedback wasn't magic at all. It was memorization. The models performed so well on older benchmarks simply because they'd seen the questions before in their training data. When faced with truly new problems, that special ability vanished. This work is a crucial reminder for the field. To get trustworthy results, we must evaluate models on clean, uncontaminated data. That's all for this week's AI Research Roundup. Thanks for tuning in.